This is Chapter 2, Lecture 2. We're on page 9 in the notes, and we're going to look at scientific notation. Scientific notation expresses any number as a number between 1 and 10. This is known as a coefficient. And that number will be multiplied by 10 raised to some power, which is known as the exponent. To put a number in scientific notation, we move the decimal so we end up with a number between 1 and 10. In this case, we will put the decimal between the 4 and the 6. We then simply count how many places we had to move the original decimal to get to that point. So in this case, 3, 6, 9, 12, 15, 18, 21, 22, 23. So we multiply it by 10 raised to the 23rd. If we have a number less than 1, we follow the same process. We put a decimal so that we end up with a number between 1 and 10. In this case, it will be after the 2. So how many places did we move the original decimal? 3, 6, 9, 12, 15, 18, 21, 22. It's also 23. So times 10, but this time to show that the number is less than 1, we say negative 23. Flip ahead to page 16 in your notes. Where we're going to look at accuracy versus precision. Accuracy is how close a measured value is to an accepted value. Precision is how close a series of measurements are to one another. So if you look at the picture of the 4 targets, in the first picture, we have one arrow that was thrown, and it was accurate because it hit the center target. But we cannot comment on the precision because there's only one arrow. In the second picture, there are 3 arrows that landed very close to each other, so they are precise. So they are precise. But because they missed the target, they are not accurate. The third picture shows 3 arrows that are close together, so they are precise. And since they hit the target, they are also accurate. The fourth picture, where the 3 arrows are just dispersed all over the place, are neither precise nor are they accurate. To apply this to chemistry, if a measured mass is weighed as 2.63 grams one time, 2.63 grams a second time, and 2.62 grams a third time, which is still pretty close. And the actual mass is equal to 2.63 grams. Then this measurement was both precise, because all 3 values were close, and it was accurate because the measured mass was close to the actual mass. If the actual mass was 3.79 grams, then the 3 measurements would still be precise, but they would no longer be accurate. Turn to page 17. Whenever we measure, we usually have some sort of error in our measurement. Error is the difference between the experimental value and the accepted value, between what you get and what the actual answer is. Percent error has a formula. Percent error is equal to the difference between the two values over the accepted value times 100. So if we look at the problem, they ask us to calculate percent error using ESA. Percent error is equal to difference over accepted times 100. So the percent error is equal to the difference between 2.34 and the actual mass of 2.01, which is 0.33, over the accepted value, which is 2.01 grams, times 100. So using your calculator, the percent error is equal to 16.4%. And we're going to finish with a quick video on scientific notation.
In order to write these numbers in scientific notation, they need to be in the form of A times 10 raised to the power of B, where A, called the significand or mantissa, is greater than or equal to 1 and less than 10. So to rewrite 15,600,000 in scientific notation, we first need to determine where we'd have to place the decimal in order for A to satisfy this condition. Right now the decimal point is here, and in order to satisfy this condition for A, the decimal point would have to be placed here. Now by counting the number of decimal places from here to here, we can determine the exponent on 10. So we have to move it 1, 2, 3, 4, 5, 6, 7 places to the left in order to satisfy the requirement for the value of A. Therefore, written in scientific notation, we would have 1.56 times 10 to, we move the decimal place 7 places to the left, so our exponent will be positive 7. Now sometimes it's difficult to remember whether this exponent should be positive or negative, and here's an easy way to remember. If we start with a large number, like we did here, 15,600,000, in order for this to equal a large number, this exponent here will have to be positive. Multiplying by a positive power of 10 will make 1.56 larger. Now let's convert a small number to scientific notation. Again, the first step is to determine where the decimal point would have to be in order to satisfy this condition here for A. So the decimal point would have to move from here all the way to here to make 8.72. Now let's count how many decimal places we have to move from here to here. It would be 1, 2, 3, 4, 5. Which means in scientific notation, this would be equal to 8.72 times 10 to the, because we move the decimal to the right, it's going to be negative 5. Again, to me, moving right and left gets confusing as to whether the exponent should be positive or negative. If you can just remember that the original number was very small, then multiplying 8.72 by a negative power of 10 is going to make a very small number like we started with.